Hi guys. Okay, this is a video that I made going over the basics of encryption for programmers. Encryption is such an important topic in digital forensics and cybersecurity that it's really worth spending some time going through some examples and learning how it really works. And you need to start with the simplest form of encryption and kind of understand how that works, and then gradually work through increasingly more complex encryption algorithms. So for this one, I'm going to start with the most basic form, which is shift ciphers. I'm going to give my introduction here and give programming examples in Ada. And I know Ada is a language that most people don't really see that much of. It's mostly just used for safety critical real time control systems in the aerospace industry. But that's where my whole software career was. So that's kind of the language that I saw the most. But you can do this with any programming language, and the logic of what's going on is really the important part. And the syntax in Ada is very readable, so it should be easy to see how you would adapt this to whatever programming language you like. So the shift cipher is the simplest and one of the oldest uses of cryptography, and it's believed to have been used by Julius Caesar. Each letter in the plaintext is shifted over by some number of letters, and then the message can be read just by shifting the letters back by the same number. Today, this is not a secure method. It's the easiest form of cryptography to decode. Each letter is shifted by the same amount, and the lengths of words are clearly visible, and that makes it vulnerable to frequency analysis. Basically, the most commonly used letter in the English language is the letter E. So if you take your encrypted text and you count the occurrences of each letter, the one that gets used the most is probably going to be the letter E. So then based on that, you can see how far the encrypted letter E is shifted away from the actual letter E, and then you can use that number to decrypt the entire message. That's not the method that I'm going to use in this example, but that's another one that's easy to do using a shift cipher. So the way this works is you're going to replace each letter with a number P that is one less than its position in the alphabet. Then to shift by some number K, f of P equals P plus K mod 26. That just means that the position of the new letter will be the position of the old letter plus the amount you're shifting by. Then you're going to do the mod 26. That's just dividing by 26 and looking at the remainder to see where it falls within that range of 26 letters. And then doing that, to decrypt, you just use the inverse function. So f inverse of P is just P minus K mod 26. So before I go over my strategy here, I'm going to show the basic example of that. Since we know there are several different types of encryption algorithms, that kind of sounds like an object-oriented solution. So here I create an abstract base class that I'm going to derive all of my different encryption types from. And it's just going to have a plain text and a ciphertext. And when you create one of these, you're going to know one or the other, and then you're going to use your algorithm to fill in the one that you didn't know. So I've got my constructor and my encrypt and decrypt methods here. Then the first one that I'm going to derive from that is my shift cipher. And this will inherit everything from the base class cipher type, and it will add an integer for a shift, which is the amount of shift that you're using to do the encryption. So then I've got my constructor algorithm here. Then I've got my encrypt and decrypt methods here. So to do the encryption, I'm taking my input from a string. I'm going to loop through each character in the string. Since we're looking at the position within the alphabet, but the software is going to see it as an ASCII character, I'm doing a little adjustment here to adjust the ASCII character value into the range of 0 to 25 just to find the position within the alphabet. Then once I've done that adjustment, I just have my number for the position within the alphabet plus the shift amount, and then the mod 26, and that gives me the new character. The decrypt algorithm is exactly the same thing, except that instead of adding the shift, here I'm just subtracting it. So then for my encrypt program here, from the command line, I'm going to give it a number for how many characters I want to encrypt, and I'm going to give it a file name that contains the data that I want to do the encryption on. So I'm going to validate my input and make sure I've really got a numeric value for the number and a good file name. Then, while it's not the end of the file, I'm just going to read the file and put the data into this message string. And then here's where I create my shift cipher object. And I'm going to tell it in this case that I know the plain text, which is contained in this message string. And I've got a value for how much I want to shift by. Then I'll do my encryption, and that will fill the ciphertext string with the encrypted version. And then I can just output that. And then the decrypt procedure will work the same way. I'll just take in my inputs for a number that the shift is done by and a file name. Then it just gets the text out of the file, creates my object, does the decrypt algorithm, and then puts out the plain text. So if I go into my first directory here, I've got my text file. This will be the data that I'll use. This is test data for the program. We suspect the data will be encrypted using a shift cipher, but we aren't sure, and if so, we don't know the length of the shift used. If it is a shift cipher, we should be able to find the correct way to decrypt the data. So using this, I've got my encrypt algorithm here. I'm going to give it a number that I want to shift by. I'll say 4 for the first example. And then I've got my input file. That's my data1.txt. So here it shows what that looks like with the input file shifted over by 4 letters. So I can do that and put the output into a data4.txt file. And then just to have another example to work with, I'll do it again and I'll shift it over by 7. Here's what it looks like shifted over by 7 letters. So I'll put that into a file here and call it data7. So now when I want to do the decryption, it works the same way. So I've got the one that was shifted by 4. Here's what it looks like when it shifts it back. Then I've got the other one I did by 7. And it's really that simple. But what do you do if you don't know how far it's been shifted? If all you have is the encrypted data, this is what it looks like. So if you want to find the way to decrypt it, you have to figure out how far it's been shifted. So I've got my strategy for that here. If you have an encrypted text, how can you determine if it was encrypted using a shift cipher? Word lengths will still be visible, and all letters are shifted by the same amount. And you might see common 1 or 2 letter words which occur several times within the text. So if I look at it here, I can see some 1 or some 2 and 3 letter words. There are several 2 letter words, so that's what I'm going to work with here. Some 2 letter words are so common that will be seen frequently in any text, so I've got a list of them here. So you can build a list of common 2 letter words, and for each word, track the difference of the position numbers for the 2 letters. Then you can find 2 letter words in the ciphertext and compare the position differences to words in your list. So some examples here, I've got common 2 letter words and how they look like when they're shifted over by 3 letters. So if you look at the position difference between the I and the F in if, here it's shifted over by 3 letters, but the difference between the positions will be the same between these 2. So that's what I'm going to work with to try to determine how far it's been shifted. So I'm going to build a list of all the 2 letter words in the ciphertext and find the position difference between the 2 letters for each word. Then I'm going to compare this to a list of known 2 letter words. When matches are found, I'll find the position difference between the plain text word and the ciphertext word. That might be the shift, so then I'll use that value to shift the entire list and look for other word matches. So I need a solution that will be easy to modify later when we want to add more complex processing. Other encryption algorithms will be more complex and will require more complex processing to be done. So the solution has to be one that makes it simple to add more processing as the problems grow more complex. So here, I could just go in and throw in some code that will pull out a 2-letter word and then compare the difference to words in my list. But then each time I come to a new encryption algorithm and have to add more complex processing, if I just take the same approach and kind of throw in some more code to do what I need for this one, after you've made a few updates that way, you end up with a big chaotic jumble of code, and it can be really hard to work with. And you'll have the same variable used in so many different places that it's hard to keep track of everywhere that it's changed. And then if you put that away for a few months and then come back to it, it just looks like a big chaotic mess, and you have to spend a lot of time kind of relearning how the code works. And I don't like that approach, because as I'm going through different encryption algorithms, I already know I'm going to have to add more complexity each time. So I want a solution where it will be really easy for me to make updates to. So basically, I want to organize my processing logic in a way that makes it really clear what each little block is doing and makes it really simple to go in and add more later. So if I define the problem I'm looking at, given a text file of unknown length, we want to scan through the file one character at a time and build lists of all the words in the file. And I've decided I'm going to make separate lists for words of 1 letter, 2 letters, and 3 letters. And then all words with more than 3 letters will go into a 4th list. And I need to ignore spaces and punctuation symbols while doing this. And this kind of sounds like a problem for using a deterministic finite state automaton, which means I'm going to describe the problem in terms of a set of states the system can be in while it's processing, a set of inputs that will be processed, and a set of criteria for transitioning from one state to another based on the current state and the current input. This will give me a simple way to process the inputs to build our word lists, and it will be simple to modify later when more complex processing needs to be added. So we've got our formal definition here. A deterministic finite state automaton has these 5 elements to it. Q is a finite set of states that it can be in while it's processing. In this case, that will be things like it's found a non-word character, or it's found a word character, or it's found the end of a word. And then sigma here is a finite set of inputs called the alphabet. This is all the different characters that it might see in the alphabet and have to process. Then delta is a transition function from some state in Q and some input within the alphabet to another state within Q. Then this Q naught existing within the set of states is one that's called the start state, where it will begin each time it's starting to process for another word. And then F here is a non-empty subset of Q called the final states. And this is a really simple example, so there's only going to be one final state, and that's when it's found the end of a word. So for my finite set of states, I've got a start state ready for input. I've got one for processing non-alphabetic characters, one for processing a word, and one for where it's found the end of a word. For my input alphabet, I need to process all upper and lowercase alphabetic characters and common punctuation. I've made an arbitrary choice to include all ASCII characters from the space character ASCII 32 to the closing brace character, which is ASCII 125. Accepted words will be only alphabetic characters, and all others will be treated as non-word characters. So I made a state transition diagram. I just took a photo of my little diagram here. I hope this is sort of visible here. I've got my 4 states ready for input, found non-alpha, found alpha, and found the end of a word. So it starts here in state 0. And if the character in the current input is alphabetic, it goes to this found alpha state. And then as long as each new character is still alphabetic, it just keeps staying in this state 2 until it finds a non-alphabetic character. Then it goes to this final state where it's found a word. But from the start state, if it finds a non-alphabetic character, it comes to this non-alphabetic state. And then as long as the current input continues to be non-alphabetic, it stays here until it finds an alphabetic character. Then it goes up to state 2 and processes until it gets a non-alphabetic character that shows it's at the end of a word. So from this diagram, I can build a state transition table. So here I have all of my possible states and all of my possible input types. And based on the current state and the current input, it can look up where the next state will be. So in my code, here's my package spec. This is kind of like the header file in C. This just defines the data that can be used by the calling program. Here I've got just unbounded strings for my 4 lists of words. These will be for words that are 1 letter, 2 letter, or 3 letters, and then everything else will go into the 4-letter list. And then I've got a procedure scan that will take the input and do the processing. So if I look at my scanner here, this is where I implement my diagram and my state table. So I'm going to define an input type as either alphabetic or not alphabetic. That corresponds to the inputs on this state table here. Then I'm going to define a state type for ready, non-alpha, alpha, or end of word. Those correspond to my input, or to my states here on the table. And then from there, I just build my array here. This will be my table where I can look up, based on the current state and the current input type, I can look up what my next state needs to be. Since I need to identify uppercase or lowercase characters, I declared these subtypes here. This just means that these are a subset of type character, because the type character includes all of the ASCII characters, and I need to be able to tell if it's in the range of lowercase letters or uppercase letters. So by defining this subtype here, that means that all I have to do when I come across a letter is just see if it's within the range of one of these subtypes. So then to do the processing, I've got my current element, which is the first one in the data. And here's my main processing loop. Finished will become true when the end of the input data is reached. So I've got my while not finished loop here. I'm going to get the first state based on the data and the index. This will be my input character, and then I'll make a determination if it's alphabetic or non-alphabetic. So then I have my case statement where here I get the current state by looking at the state table based on the current state and the current input. So here's my start state when ready. That just corresponds to this state 0 here. If it's ready, I'm not going to do anything because I'm just going to move on to the next character. If it's non-alphabetic, I'm not going to process that because we're throwing those out, so I'm just going to increment my index to look at the next character. If it is alphabetic, I'm going to keep track of how many alphabetic characters I found for this word, and I'm going to add the current word to a temporary string and increment my index. Then it will keep coming back to this state until it finds a non-alphabetic character. Here, when it's found that non-alphabetic character, it leaves state 2 and goes to 3. So when it's at the end of the word, based on the number of letters I've counted, I'm going to put it in one of these lists. Then I'm going to reset my letter counter. I'm going to reset my temporary string and put the state back to ready. And then if my index is at the length of the data, I set finish to true and it exits the loop. Otherwise, it just goes back through the case statement again, and it keeps repeating until it's at the end of the input. So once that's finished, these word lists here will be filled with all of the words sorted by how many letters they are. So then I can get on with my strategy for trying to decrypt it. Now that we have the encrypted data parsed into lists of words organized by word length, we'll use this to attempt to identify how much of a shift was used for the encryption. A shift cipher shifts every letter by the same amount, so if we can find the correct number for one word, it should work for decrypting the entire message. So I'm going to use my list of 2-letter words. I'm going to build a common list of 2-letter words, and for each word, I'm going to record the distance between the 2 letters in terms of their position within the alphabet. Then I'm going to find 2-letter words in the ciphertext and find the distance between the 2 letters for those. When a ciphertext word has the same letter distance as a known word, then I'll find the distance between the ciphertext letters and the corresponding plaintext word letters. Then I'll try shifting the entire text by that amount to see if that turns out to be the actual shift amount. So if I come back up to my examples here, for all of my common two-letter words, I'm going to keep track of the distance between the first letter and the second letter. So then when I find an encrypted word that's two letters and has the same distance between the first and second letters, I'm going to call that a match. So then I'll see how much the letters in the encrypted version are shifted away from the real word. Then I'm going to try using that number to shift the entire message and see if that comes out as a readable plaintext message. So for my word list spec, here I've got my list of two-letter words. I'm building an array with all of these. And then I'm going to have a record here for each one. I'll keep track of the word and the distance between the two letters. And that's what I'm going to use to search for a match. So then in my processing file here, I'll have functions to do the processing that I need. I'll have one to get the distance between two letters. I'll have a function to get a word out of the list based on the length and the index. Then I'll have one that returns true when it finds a match between an encrypted word and one that's in its list. And then I'll have one to return the shift value that it found. So then using that in my main program here, I'll open up my file. This will be a file that contains the encrypted text. So then I'm going to read until the end of the file and add all of the text to my message string. Then I'll scan my message here. And after this call to scan message, all of the words in the encrypted text will be parsed into these word list variables. So once I have that, I can loop through all of them and see if I find a match. And if so, when it finds a match based on the distance between the letters, that's where I'm going to create my cipher shift object here. I'll tell it that I already know the ciphertext because I'm reading this encrypted text. And the text will be contained in this message string, and the shift value to use will be the one that it found in this match found procedure. And then after that, it will just show me what shift it identified, and it will show me the encrypted text, and then show me the decrypted version so I can see if it looks like a match. So I'll go down, okay. So these are the two that I got when I tried to encrypt my message. I've got it shifted over by 4, and I've got it shifted over by 7. So I'm going to copy those. Oops. Okay, so now I've got my encrypted versions here. Here's what the text looks like unencrypted. Then I've got one version where I shifted it over by 4, and I've got one version where I shifted it over by 7. So using this, I'm going to try my scan file, I'm going to try my scan file program on data 4. So it was shifted over by 4, so it's going to try to identify how far it was shifted and what it looks like if it unencrypts it by that amount. So here it identified the shift as 4. Here's what it looks like encrypted, and here's what it came up with unencrypting by shifting back by 4. So then I can do the same thing with the one that I shifted by 7. And again, it identified the shift as 7 and shows me what it looks like unencrypted. Because there are a lot of two-letter words in here, so when it found this PZ, it recognized that the difference between those two letters is the same as the difference between the I and S and is. So then it just found how far that was shifted from here, and it used that to shift it back. And when I go back to explore more complex encryption algorithms, the processing will be more complex, but it will be really easy for me to just add more possible input types here or more possible states, add another state to my diagram here, and then just go back to my case statement here to insert the processing for any new states that I have to add. And I know that all the encryption algorithms I'll look at after this will be more complex, so I'll have to add more things to here. But it will be simple to do because I designed it this way. But for shift ciphers, this is really all there is to it. So that's all for this video. So thanks for watching.